Hayes, and today we're going to be introducing Cellular IoT on the NRF 9160 system and package with Rust programming. So the first thing we're going to do is we're going to introduce the hardware. As I just mentioned, we're using the NRF 9160 from Nordic Semiconductor. This is a system and package, which means that it has two processors. Both of those are ARM Cortex M33. It has 1 megabyte of flash, as well as 256 kilobytes of RAM. It supports LTE-M, NB-IoT, and GNSS. And of course, it is certified for global operation, dedicated application processor. That's what I just mentioned. It has two processors. One will hold our Rust application and communicate with the other processor, which holds the firmware for the cellular modem. And it supports ARM Trust Zone as well as ARM Crypto Cell. So that's the system and package. That's the chip. And the development kit that we're going to be working with is from Connexio Technologies. And this board is called the Connexio Stratus. It's a fantastic little development board. On the documentation, here's the pinouts. Let's see, it's got USB-C. It's pre-programmed with the MCU bootloader. That's mainly used for the Zephyr SDK, so we won't be using that, but it comes preloaded with that. We have a energy harvester IC on board. It's an AEM 10941 from EPs. That works really good. I've used that with a solar panel as well, and that does work very well. It has a 10-pin JTAG connector, supports J-Link and Simsys DAP programmers, debugging probes. It's got some onboard sensors for development, and you can also get an optional shield to help you connect other types of sensors that you want to mess around with or develop with. And so yeah, this is the development kit that we're going to be using. It does come with the Once IoT SIM card, preloaded with 500 megabytes of preloaded data. I've used that and it works well in my area. I've also used the TruePhone SIM card, and that one works well. That one works very good as well, but it may depend on your area which SIM card that will work best for you. So that's the hardware that we're going to be using. If you don't have a Connexio Stratus development board, I highly recommend grabbing one. Otherwise, you can use the Thingy 91 development kit from Nordic, as well as an Actinius Icarus. And this should work with the NRF 9160 development kit from Nordic. I have not tested it myself. It should work, but it may be a little extra work on some of the applications we're going to be looking at. But the Actinius Icarus and the Thingy 91 have both been tested with this application code that I want to show you, and they all work. So the first thing that we're going to do, the Goliath RS project, and you can come here and copy that code and then clone it into your project directory. Notice that we do have to have a nightly compiler to use Embassy. Okay, so we've already mentioned the MCU bootloader. So when we start flashing our Rust programs, we are going to overwrite the MCU bootloader. So if you test this stuff out and decide that you need to use the Zephyr SDK, you'll have to flash that bootloader back. And one of the easiest ways to do that is just to go to the Nordic website and download their pre-compiled firmware packages that has the bootloader included, and you can just flash that on the board. Also notice that we need a secure partition manager, SPM, and the SPM is a bootloader-esque kind of binary that's going to get us into a non-secure context when we jump to our Rust code. And when we use the modem library, we have to be in a non-secure context. Embassy has the ability to run from secure mode. However, we cannot interact with the modem in secure mode. Therefore, we have to include an SPM, which you can build your own with the West tool from Zephyr if you want to. And I think they have a newer version called TFM. But for simplicity, I've included a precompiled SPM right here. It's under the zephyr.bin file or zephyr.hex. The library that we're using for the modem is closed source and developed by Nordic. So since it's closed source, it makes it much harder to reverse engineer. Therefore, we're going to be using the NRFXlib syscrate, which is basically a Rust wrapper around the C library. In order to use that, we have to install a couple of dependencies, and those are Clang for LLVM and ARM-GCC toolchain. The Clang part is required for our bindings, to generate our bindings to that library, and the GCC ARM EABI is required for building TinyR-libc, which is required for some of the types to interact with the modem library. So here's the instructions for installing it on a Unix-like system. I'm using Pop! OS in this tutorial, but you can also do it on Windows, and you just follow these links here and double check everything with version. And so once you get that installed, we're going to install a couple of cargo components. The first one is FlipLink, which flips the stack during linking. It's a method for overflow protection on the stack. We're going to install probe run, which is going to be the runner for our, when we run cargo run, it's going to invoke probe run, which will allow us to run the program on our development kit and not on the host computer. As I mentioned, MSC requires a nightly compiler, and that's going to be handled in our Rust toolchain.toml file. And if we look at that real quick, we can see that the official approved channel for the nightly compiler is the 2023 0518 version. And we got our components here that we're using and the target. So that will take care of setting the correct tool chain when we build. We need to install the correct target. So we're cross-compiling because this binary needs to be compiled for our development kit and not for our host computer. In the case of the Cortex M33, that's this target triple right here. So we're going to install that target. And once we do that, we should be ready to start building programs. Before we run any kind of programs, I want to kind of go through the directory here and kind of point out some files and just kind of see how this project's laid out. And the first one we're going to look at is the config toml, which is in the .cargo directory. In here, we're saying that our target has the ARM architecture and does not have an operating system. Here's our run command. This is what's going to be invoked when we do cargo run. So that's where we installed probe run component, and then we're going to tell it that this is the NRF9160 chip. We have an environment variable set here for our deformat, which is our logging framework, and we can set a different level, debug, info, error. Here we're defining the target triple, which is our target for cross compilation. And here we got a neat little feature called alias. And what we can do is we can define shorthand commands for longer ones. So we can say build binary, build release binary, and we can define it as a shorthand like BB, BRB, that kind of thing. So that way we don't have to type it out every time we want to run something. Notice up here that we have a couple of commented out Rust flags. So there's two different ways to pass the compiler flags to Rust up or Rust C. And one of them is to put them in here in the config.toml. I prefer to put them in build rs file. So in the build rs file here, we've got a few some code that I've copied from another repo. And it basically just makes sure that if we have a more complex directory, that we can find the memory.x file, which we'll look at here in just a minute. And then down here, we're going to pass in those compiler flags. There's the flip link flag. Link.x is our linker script. That is in the Cortex M crate, I believe. Deformat, that's just saying that to pull in the deformat debugging symbols. And then in Magic, that's just memory addresses aren't aligned in a certain manner. If you are more curious about that, you can just look at this pull request here. Well, the first time I saw this build RS in use, I was looking at these print lines and I'm like, oh, this ain't doing anything. And I know it just looks like it's just printing this text off, but that's actually how it passes these flags to Rust C, is actually through the print line macro. The next thing we're going to look at is our memory definition file. So it's memory.x. And this is just like I say, it's a definition file of our memory layout. So we've got a section here named SPM, and that's where we're going to be flashing that secure partition manager that's going to get us into that non-secure mode. And notice that it takes up a lot of memory. It's unfortunate, but that's the way it is. And here's our flash and RAM definitions, and a little extra linking section here to get that SPM linked in correctly. Now for our cargo.toml file, this is where we're going to put all our dependencies on other crates. I'm not going to go into this too deep. We can control our build based on certain versions of other crates with features. Embassy does not have an official release. It does not have a 1.0 release yet. We're going to be basically patching in from the GitHub profile. So here we have our Embassy crates and our dependencies and feature flags, but then we're going to patch it from GitHub. Down here we have build profiles to set different settings based on how you want to build. We've got a profile for development, one for testing, one for release, and one for bench. And this is not required, but this is just to show you how you can change optimization levels and debug symbols and how the compiler works based on if you're doing development building or you're building for production with the release profile. So what I'm going to do here is I'm going to run cargo clean, and that's going to clean out my builds, all my previous builds. And then I'm going to invoke a longhand command, cargo. We're going to just build for now, and we want a bin AT client. All right, we got our first build. We say we've optimized it. We've got our debug info. Fantastic. So everything built without problem. So we know we've got all our development environment set up correctly. And what I want to show you now is how to use those alias commands. We're going to say cargo build release binary AT client. So now this is going to build the release version of AT client using the shorthand command. All right, we got our optimized release version built. We are completely ready to start flashing programs to our development kit. We'll do that in the next video. We'll go over how to set up a debugging probe so we can flash to the target. We'll get all that set up, and hopefully we'll run this AT client program, which is going to allow us to send AT commands to the modem and begin learning how to set up the modem and how to use that to connect to a cellular network. I appreciate you guys watching the video. I hope you enjoyed it, and I'll see you in the next one.